Hey everybody, in this video we're going to talk about integration by parts. This technique is particularly helpful if you have a product of two functions in the integrand. This is actually based on or developed from the product rule for derivatives. So we're going to talk about how we develop this technique and then look at some examples. So let's consider two functions of x. We'll call them u of x and v of x. If I want to get the derivative, I would take the derivative with respect to x of the product of those, u times v. I'm just going to call them u and v for short. So this would be the first times the derivative of the second plus the second times the derivative of the first. So here we have the product rule. And next thing that we want to do is basically undo this with taking the integral of both sides with respect to x. So like this. Now, on the left side, we differentiated with respect to x and then anti-differentiated with respect to x. So we'll just end up with uv on this side. On the right side, you have a sum inside the integral. So I'm going to write this as the integral of u dv dx plus the integral of v du dx. Now, an interesting thing here, we can kind of cancel these dx's in each integral. So this is the integral of u dv plus the integral of v du. That's the product u times v. Now, if we rearrange this a little bit, we could rewrite this as the integral of u dv equals uv minus the integral of v du. So notice all we did was solve for this integral, but I put it on the left-hand side. And this is actually the integration by parts formula. The integral of u dv equals u times v minus the integral of v du. In f and g notation, how we can think of this is f times g prime equals f times g minus the integral of f prime g dx. So here's our first example using integration by parts. The first thing you want to do is identify what the u. Now, when you select the u, it's going to make a big difference in how you choose them. So in this case, we're going to let u equal the x and dv equal e to the x dx. Once we pick the u and the dv, you take the derivative of the u function, which is 1 dx, and anti-differentiate the other one, e to the x. And then you follow the formula. So it's, if you look at the formula up top there, it's u v minus the integral of v du. Okay, now the process here, I set it up like this in this little chart on purpose with u right here and dv right here, and then I differentiated u to get du, and I integrated dv to get v. Because when you set up your integration by parts using the formula, it's u times v minus the integral of v du. So when you have it set up in that chart, it's very easy to figure that out. Now, we're not done with this problem, but notice that in the new integral, the minus the integral of v du, it's just the integral of e to the x, which is e to the x plus c. The problem is, in the original integrand, there was that x multiplying the e to the x, so you couldn't use u substitution there. But we can use integration by parts. Now, there is a trick for identifying what to use for the u, and here it is. Your first choice would be logs. We call this LIATE. The second choice is inverse trig. The third is polynomials. The fourth is exponentials. And it's just regular trig functions. Okay, if you remember LIATE, it's very easy. So notice in this one, we picked u equals x, and u is or x is a very, very simple polynomial function. So this is our answer right here. Let's check out another example. We want to look at this formula right here, or the integral of x sine x. We're going to set up our chart here with u and dv. Again, we're going to use LIATE. So we don't have any logs, we don't have any inverse trig. We do have a polynomial function and a trig function. The polynomial gets picked over the trig, so we'll do x here, and dv is sine x dx. Then the derivative of u is just going to be 1 dx, and the antiderivative of sine, be careful, is negative cosine. And then we would do uv minus the integral of v du. So this is going to be negative x cosine x minus the integral of v, which is cosine x. So notice I changed that subtraction to addition because the formula for integration by parts is minus the integral of v du, but the cosine itself was negative, so transferred to a positive. So this is minus x cosine x plus sine x plus c. And of course, you could always check this by differentiating. So the next one we want to look at is finding the antiderivative of natural log x. So we know how to differentiate natural log, but we don't know the antiderivative. So when we're picking our u and our dv, it's probably going to be that the natural log is our u, because we have to then differentiate that. And what we're trying to do is integrate it, and we don't know how, but we can use integration by parts here. Also, if you think of LIATE, we have a log in here. And you might be asking, well, what's the dv? Well, the dv is just going to be dx, and you can think of that as having a 1 understood to be there. So du is going to be 1 over x dx, and v is going to be x. So when I do my integration by parts, it's uv minus the integral of v du. So I would have x natural log x minus the integral of v times 1 over x dx. Now notice the x's here would cancel, and you would just end up with the integral of 1. So it's x natural log x minus the antiderivative of just 1 is x. Don't forget your plus c. And there we have it. So the next one we want to look at is integrating the inverse tangent function. Going to do the similar thing that we did with integrating natural log. When we pick our u and our dv, we follow LIATE, L-I-P-E-T. We don't have a logarithm, but we do have an inverse trig function. So that's going to be our u, tangent inverse of x. And dv is just going to be dx. So du is 1 over 1 plus x squared. And v is going to be just x. Because remember, dx is like 1 times dx. So if I go uv, so tangent inverse x times x, but I'm going to put the x in front, minus the integral of x over 1 plus x squared dx. Now that integral right there looks like a log form, because if I let u equal 1 plus x squared, then du is 2x dx, and 1/2 du is x dx. So I'm just using u substitution right here. I'm defining u as a different function here. And so I'm not using integration by parts again or anything like that. So this would be x tangent inverse x minus 1/2 integral du over u. So this is going to be x tangent inverse x minus 1/2 natural log absolute value of u plus c. And u was 1 plus x squared, so it's x tangent inverse of x minus 1/2 natural log of 1 plus x squared plus c. You don't need the absolute values because 1 plus x squared is never negative. The next one we want to look at is x squared e to the x. So if we think in terms of LIATE, we don't have a log, we don't have an inverse trig, but we do have a polynomial with the x squared. So u equals x squared. dv is going to be e to the x dx. So du is 2x dx, and v is going to be e to the x. So I would have uv minus the integral of v du. So it'd be 2x e to the x dx. Now the problem here is that this integrand right here is a product again, and I can't use regular u substitution. So I would have to do integration by parts again. So here I would pick u equals x, dv equals e to the x dx, du is dx, and v equals e to the x. So you have to be careful because you have the x squared e to the x, and I factored that 2 out, but it's a -2. So I have to multiply -2 times the result from the integration by parts. So uv minus the integral of v du. Okay. So if I clean this all up, I would have x squared e to the x minus 2x e to the x, because I'm distributing this 2. And then the 2 is going to multiply into the next integral, which would be minus 2 times the integral, or plus 2 now, of e to the x, which the antiderivative of e to the x is e to the x plus c. Now, if you notice in the heading for example 5, it says the tabular method. There is an actual way that you can do these ones where you have repeated use of integration by parts. And typically it's going to occur whenever you have x to a power times a function that kind of revolves in its derivatives. So like e to the x keeps having the same derivative or antiderivative, and same with sine and cosine. So here's how we do this. We set up alternate signs, and I'll show you what I mean in a second. And then we have u and dv, okay? So we always start with plus. And in the same thing here, we had u is x squared and dv is e to the x. So what you do is you just differentiate the u until you get to 0. So 2x, 2, and 0. And then you alternate the sign every time. And then the dv you integrate. Well, it's going to be e to the x each time. And then you start and go, it's going to be plus x squared e to the x, so x squared e to the x. And then you move down, you do the same thing, minus 2x e to the x, and then plus 2 e to the x. And then you don't forget your plus c on at the end. And notice we got the same answers here in both cases. Now this last row, you don't have to do anything there. Here's one with a trig function and e to the x all kind of put into one. So if we think of LIATE, we don't have a log, we don't have an inverse trig, we don't have a polynomial, but we do have an exponential. So u is going to be e to the 2x, and dv is going to be cosine 3x. So we start with alternate signs, plus. So we take u, the derivative is going to be 2e to the 2x. Derivative again is 4e to the 2x. Then we would have 8e to the 2x. The problem with the table method here is that e to the x never ends up going to 0. And if we looked at cosine, when we anti-differentiate cosine, you would have sine of 3x times 1/3. And the antiderivative of that is negative cosine of 3x times another 1/3, which would give us 1/9. And then the antiderivative of that is sine of 3x times another 1/3, which would be negative 1/27. You see, even if you use the table method here, it's not going to get anywhere. So I want to show you what happens in this situation where you kind of have a integration by parts problem, but when you start doing it, it's like it never ends. So again, we're going to follow the same LIATE and let u equal e to the 2x. So the derivative is 2e to the 2x dx, and v would be 1/3 cosine, or excuse me, sine of 3x. And then the uv is going to be 1/3 e to the 2x sine of 3x minus the integral of v du. So the 2/3 would come out front, and we would have e to the 2x sine of 3x dx. Now we're going to do integration by parts again, and let's see what happens. The u again is going to be e to the 2x, and the dv is going to be sine of 3x. So du is again 2e to the 2x dx, and v is going to be negative 1/3 cosine of 3x. Our problem now becomes 1/3 e to the 2x sine 3x minus 2/3 times the integration by parts. So e to the 2x cosine of 3x times 1/3 times the negative 2/3, which would give us actually positive 2/9. Then you would have minus the integral of v du. Now we have to be careful here because by the integration by parts formula, we have a minus. Then there's the subtraction there and the negative from the negative 1/3. So it's going to actually keep the minus there. So be minus the integral of v du, which is 2/3 times the 2/3 that was already out here. So you would have 4/9 e to the 2x cosine of 3x dx. You might notice that the integrand is back to where we started. If I rewrite the original problem here, these are equal. What I can actually do is take the integrand, or the integral, from the right side and bring it over to the left and have it combined, because those are like terms. So you have 4/9 plus one of them. 9/9 plus 4/9 would be 13/9. So you have, then you would multiply by the reciprocal of 9/13. Integral of e to the 2x cosine 3x dx is equal to 3/13 e to the 2x sine 3x plus 2/13 e to the 2x cosine of 3x plus c. There you go.